Hello, my name is Andrew Penner, and I'm the president of the AEE Canada East chapter. Sponsors are so important to chapters like ours. They enable us to fulfill our mission financially. Through their support, they confirm our relevance, they provide credibility, they expose our members to new ideas and ways of thinking, and of course, they help to grow our network and influence. What you see on the screen here is the current chapter sponsors for 2024. So there's a great stable of companies there with a broad range of focuses, services, and otherwise. We're pretty proud of this group, and we've been blessed to have them there supporting us along the way. If you don't see your company on the list and you think it should be there, we're always looking for new partners and new ways to engage. So please reach out. Of course, as a chapter of the Association of Energy Engineers, the AEE Canada East looks to espouse the mission and values of AEE. We are the local expression of AEE, and for some represent their sole window into the International Association. As an association, it was founded in 1977, so it's been around for a good long time. It's grown to include more than 18,000 members across over 100 countries, and there are more than 90 chapters just like ours doing work like this around the world. You can get more information about our chapter at the link there on the screen. All right, without further ado, on to today's webinar topic. So it's a case study conversation about a monstrously large smart building conversion, hailed as the largest of such conversions in North America. And our presenter today, his name is Josh Lewis. So Josh is the VP of Energy Engineering at NERVA Energy Group. He is an award-winning energy advisory firm and specialty contractor providing smart building optimization. And they leverage niche expertise within IoT technologies to ensure buildings function more intuitively and efficiently, creating energy earnings and carbon reduction opportunities. And by fostering a positive impact on occupancy, quality of life, and overall environment. So all of these things, it goes without saying, if you improve efficiency, you're often also influencing and impacting comfort. And of course, the people that are using the buildings benefit from that most. Josh, as an individual, has been recognized by a number of organizations, and he's received awards from AEE and CAGBC and others. I won't list them all, but rest assured, he's been in the business for a good long time and has lots of great things to say. So, Josh, why don't you steal the screen share from me? I'll hide myself, and the floor is yours.
All right. So welcome everybody who's joined this webinar today, or also if you're viewing this, the recording of this at some point into the future. So I am here today to talk about the largest multi-residential smart building conversion. And this was done by NERVA for Drulo Lifestyle Apartments. For those of you who are not aware of who Drulo is, they are the 10th multi-residential owner operator in Canada. They have 85 plus buildings, slightly over 10,000 suites within their portfolio, covering about 13.3 million square feet. And to give you an idea, a preview of what NERVA delivered for Drulo as part of this project, there is millions of dollars in annual utility savings, coming in at a 16% return on investment with a 36% greenhouse gas emissions reduction across their portfolio. So some pretty impressive numbers, but of course, let's not stay at the high level. Let's drive into the details to see what was done, how this was accomplished, and how the results further improve their portfolio. So just a little bit about NERVA here at the start. So NERVA Energy, we are an engineering firm. We have 80 plus staff. We've been in business 7 years now. And definitely one of our specialty areas to service for our clients is multi-residential. And you're going to see that through the case study here on this project. But like what we're doing here, what we've done here for Drulo, and we have done with other apartment owners, and are continuing to expand the reach of this, given the benefits. And like what really makes NERVA different is that while we are an engineering firm, we bring in all kinds of expertise under our banner. So not just M&E engineers, but certified energy managers, experts on mechanical systems, in-house technicians to deploy technologies, as well as energy auditors. So we really are different because we provide practical, proven, and guaranteed energy performance solutions for large buildings. Not just multi-res, but across the whole portfolio of large buildings. And this, we really feel, makes us different because we're filling a niche here in the market of the idea that we have to understand that most owner operators don't necessarily have the time or necessarily the knowledge to connect all the dots between architecture, engineering, energy, tendering, installation, commissioning, warrantying, guaranteeing the performance of their energy projects. NERVA closes that gap because we bring all of that accountability under our banner and work with the client directly using subcontractors where appropriate to bring these holistic solutions. So one fact here, the data that we've collected on hundreds of multi-res buildings show that there's up to 50% energy waste within the current operation of these buildings. So waste that can be primarily driven out of the buildings by operating them better before we even think about fuel switching. And you're going to see kind of our thought process on how that rolls out as we get further down. But the fact is that this waste is the low-hanging fruit and can easily be eliminated while achieving positive financial returns, not just on the project today and the simple payback or escalated utility cost escalated payback on this, the first step, but also in terms of returns on future decarbonization activities, future fuel switching activities. So let's just get an idea of who Drulo is. So their portfolio of multi-residential buildings is centered on London, Ontario, where they have approximately 15 buildings. But as you can see here, it actually stretches in a fairly straight line between Sarnia and Burlington. So if you can imagine that part of Ontario, you draw a line from Sarnia heading southeast. It will intersect London. It'll go through the Kitchener-Woodstock area and eventually end up in and around the Burlington area. So that's where they've built this extensive portfolio of buildings, starting back from actually the 1970s. That's when Drulo as a company got started. And you can get a sense there at the bottom graphic of the age of their building stock. So they really have everything from old builds to brand new buildings. In fact, they're right now constructing 5 to 6 new buildings a year. And in terms of mechanical, there's some consistency, but not ultimate consistency. These buildings do vary in terms of the baseline mechanical systems that were implemented over the years. They have 5 buildings that are purely electric baseboard heated. There's 35 buildings that are hot water heated, but DX cooled in the suite. So the way that's set up is there's a 2-pipe system in the building that delivers hot water, but all the cooling for the suites of the building is actually done at each suite with a DX unit that is, the condenser is typically located on the balcony of that unit. They've done that typically in their smaller buildings. I mean, talking the 5 to 6 story. Their larger buildings, for the most part, are hot water heated, chilled water cooled 2-pipe fan coil systems. Very traditional, very straightforward, and very typical for older apartment buildings. Although 2-pipe hot water heated, chilled water cooled do not offer simultaneous heating and cooling every hour of the year. It's kind of one of the downsides of those systems, but a very traditional type of build. They also have 8 buildings with hot water, simply baseboard radiators, even an older type of build in the multi-residential sector. So no cooling provided to the suites, essentially only cooling through tenant installed window shakers or floor mount units. And they actually have also as well 2 buildings with PTACs, which is less traditional in the apartment sector, more traditionally been seen in hotels, smaller hotels, not necessarily larger hotels, but They also have 2 buildings there. So there is quite a profile of their buildings, and the goal of this project was to optimize all of these different types of systems to the best of the to the best possible energy state, driving out as much waste as possible. So you add all the equipment together across these 85 buildings, you're looking at, over 200 boilers, approximately 36 chillers, 30 cooling towers, 96 makeup air units, which means that most of their buildings have 1 makeup air, but some have 2. 158 domestic hot water heaters, as well as over 1,000 mechanical pumps. So that was all within the scope of this project. Now, if we step back here for a second, and you're going to get more details on this as I go forward, but this is the strategy that NERVA uses with our clients to drive efficiency and decarbonization. And it's something we share with the sector because we truly believe that this is the right path for most of our existing buildings. And the idea is that you optimize first, then you conserve, then you do conversion, essentially putting the fuel switching last. And we'll see why that's the path that we promote as we get into more detail here. So what is optimization, or at least what is optimization in terms of, most buildings, and certainly the Drulo buildings that we're talking about this case study today? It's really about taking the existing mechanical systems they have, primarily the boilers, the chillers, the cooling towers, the makeup airs, the fans, and the pumps, and putting on smart controls that use best-in-class algorithms in order to get as much as possible out of the existing systems as they are installed in the building today. And the reality of it is that most buildings, as advanced as we may think the controls are within buildings, whether that be multi-res, whether that be more typical commercial buildings or institutional buildings, there still in most buildings is a gap between what we can optimally do to deliver heating and cooling to the space and optimize the mechanical plant versus what we're actually doing today. So in the case of Drulo, the installation of smart controls gets us to a point where we deliver roughly between 20 and 35% reduction in HVAC load in the buildings associated with 15 to 30% reduction in the greenhouse gas emissions, because obviously a lot of the savings are coming from reduced gas usage in the wintertime. So we're going to get into some more details going on here about how that happened. But if we think about this, and if we think about the waste within our buildings, this is the low-hanging fruit. I mean, we always used to say that lighting was the low-hanging fruit, and it was, certainly. But at this point, I don't have an exact number, but we got to figure probably 85% to 90% of the possible lighting projects that we could do are probably done already. So really, when it comes to whole building performance, the next route for most buildings goes through the HVAC system. It doesn't go through plug loads. It doesn't go through the domestic hot water system, at least not as the first step. It goes through the HVAC. So this is where our focus needs to be. And by quickly getting this reduction in HVAC load, Drulo is seeing a reduced utility liability and operating expenses. They're already seeing increased net operating income, but as well net asset value, because that asset that is producing revenue through the rents every month is actually increased in book value because the net operating income has gotten better because of the utility cost reduction. But the other thing that this step has done is it really has gained us performance insights for effective reporting, and effective reporting and performance insights really gets into the next step here, which is conservation. So there's some baseline things that we've implemented in these Drulo buildings. Again, I'll get into some more of those actual details in further slides. But after you've set up the baseline boxes or boundaries that the controls in the building are now operating at, but now you're getting so much more data. And in the case of the Drulo buildings, you know, if we think about multi-res buildings, which are generally considered a simpler mechanical than most commercial buildings, but now we're getting real-time data from every thermostat in the building. That's something that has traditionally never been available within a multi-residential portfolio. Typically, the controls, or at least the visibility in terms of the operation of the building, never extended beyond the mechanical plant in multi-res. Well, now we have full visibility, not just in the plant, but in every suite, in the lobby, in the stairwells, in the mechanical room, in terms of the temperature in the mechanical room. All of that data is now available in real time. And not only is it being used for real-time optimization, but it's also being used to look at additional opportunities to conserve. And again, we'll drive into some of those conservation steps as we go. The last step, though, is the conversion to low or zero carbon operation, right? So this is the point at a building's life, existing building's life, where you start to plan out and implement your heat pump solutions, whether that's going to be air source heat pumps, whether that's going to be ground source heat pumps, right? But this is the third step. And there's a fundamental reason for that. It's because if you size your new heat pump system, whether air or ground source, off of the operation of the building today, before you optimized and conserved, you're gonna invest too much capital in your new heat pump system, because you're gonna have to size it for the building loads, the building energy usage that we're seeing today. You'd have to do that from, if nothing else, purely a liabilities point of view. But if we've driven out 20 to 35% of the HVAC load of the building, and we have all this real-time data and historical data now from the entire building, it is very insightful as to how you can now size your zero or low carbon heating plant going forward, and really has double benefits. So not as only was there a return on investment on the initial optimization, but now we have another coupon, essentially, when Drulo or whoever owns the building goes to install a partial or full heat pump system, that system can now be safely sized lower. So you're getting savings on the front end and you're getting savings on the back end. But the reality of it is right now, the optimization and conversion and conservation is driving so much performance that now it puts you in a position where you might not start thinking about heat pumps until late 2020s, early 2030s as a baseline to start to roll those out, because you've already made such significant GHG savings. Now, don't get me wrong, no one has a crystal ball into the future in terms of carbon tax, in terms of EWRB reporting, penalties for inefficient buildings, but and a lot of those things cannot be necessarily forecasted. But it at least Drulo now knows that they're on a path to get to a point where, regardless of what political winds are blowing, or where future energy prices are going, and carbon tax, that they have a path to low and zero carbon operation that will make financial sense under many, many different scenarios. So what did this start off with? So getting into some of the specifics, Drulo Phase 1, or optimization, which is what NERVA completed last year in the span of 10 months in 85 buildings, was really full mechanical optimization, including boiler loop temperatures, chiller temperatures, chiller delta T's, cooling tower operation, the introduction of a few VFDs, and optimization of the makeup air units and the fresh air being delivered to the buildings. All of Drulo buildings are corridor pressurized and ventilated. They do not have a building yet that uses, for example, in-suite ERVs, like we've seen in jurisdictions that require higher levels of energy efficiency by base, like Toronto with the Toronto Green Standard. But we've also now using in that optimization step, we've identified energy abusers. So once we can start getting all this data out of the building, we can curb and are curbing additional energy waste through targeted installation of window and door sensors, which basically means if your window or door is open to the outside, your HVAC cuts off. And that is driven by a fact that we've seen now in the data across not just Drulo buildings, but other multi-res buildings as well. Most of the time, 5 to 10% of the tenants in a multi-res building are up to 40% of the HVAC load. So let me say that again. 5 to 10% of the tenants are using up to 40% of the heating and cooling annually. The reason is because those tenants are what we term as abusers, and abuse in most cases is leaving the windows and doors open on their suite and running the HVAC at full blast for days, weeks, months on end. And that we have to get rid of that waste. And we're getting rid of that waste through technology, through controls, and I'm not allowing those specific tenants. That doesn't mean if you open your window 1 day or 2 days, you're getting a window and door sensor. It's only for those tenants who are truly abusing their heating and cooling time over time. And you know what? I don't necessarily blame the tenants themselves, but the reality of it is, from a psychological perspective, is subconsciously humans sometimes have a hard time putting a value on something we don't pay for. And in the case of Drulo's multi-res buildings and most multi-res buildings, the tenants are not paying for their heating and cooling. They're paying for their plug loads in their suite, but they're not paying for the heating and cooling. Therefore, it's subconsciously of little to no value to them. Therefore, it's easier to waste that because it doesn't directly impact them. And that really drives down this, fundamental human nature that we have to recognize. Now, after that, we're moving into this conservation phase, right? So now with all this data, the strategic capital investments for end-of-life equipment start to become much more obvious, and the data is there to justify those on that end. One thing to keep in mind is, right, we have some pretty aggressive greenhouse gas reduction targets by 2050, basically getting to net zero as a country. And a lot of that has to be done through reductions, not offsets. So the mechanical equipment in commercial buildings has a minimum life cycle of 20 years. That implies at this point that for virtually all existing buildings, we're only going to get one more chance to touch the mechanical system when the end of life comes up. And we have to use that opportunity when the end of life comes up, whether that's 2 years from now, 5 years from now, 10 years from now, whatever the life cycle is within that building. Because if we don't, we're going to lock ourselves in for another 20 years, because under almost no scenario would it make sense to do a like-for-like replacement in a building at the mechanical plant level, like put in new boilers, and then rip those boilers out 5 to 10 years down the road, less than halfway through their life cycle. That does not sound like a good plan. It doesn't sound like a good plan financially. It doesn't sound like a good plan from an embodied carbon perspective. So we have to avoid that. And Drulo now is on that path to do that. But also using now the data driven from this project, from this efficiency project on their existing buildings to drive their new builds. Most rules of thumbs for sizing mechanical systems in buildings, and this goes all the way from the plant, the boilers, the chillers, to the pumps, the risers, all the way into the fan coils, into the suites. In the case of a multi-res building, they're typically too large. And that is just a holdover from the days when, liability from a design perspective had to be the number one consideration, but we're no longer in those days anymore. There has to be a line between liability and efficiency, both in terms of efficiency in terms of energy, but also in terms of efficiency of energy costs. And the best way to get engineers on board with downsizing mechanical systems into new buildings is to show real data. And we are actually having a lot of success with that. with the engineers that do work with Drulo, and they are actually, you know, getting very appreciative of the education they're getting with all this data, because it's not only helping them optimize their designs for Drulo, but also their other clients as well. The other thing that we're going to be looking at on a few specific Drulo buildings, not the vast majority of them, is heat recovery. This is an opportunity that actually, Drulo doesn't have a lot of buildings this applies to, but there are a lot of multi-res buildings in Ontario that do have this opportunity to really simply add heat recovery to buildings that have central exhaust. So central exhaust means that we're pulling all the exhaust from the suites, the bathrooms, the kitchens, we're pulling that up through fans on the roof, vertical ducts and fans on the roof. For any building, multi-res building that's designed that way, which, you know, is probably somewhere between 30 to 50% of all the multi-res buildings in Ontario, adding heat recovery means just putting new makeup airs on the roof that transfer the heat from that exhaust air back into the makeup air going back into the building. That was something that was never traditionally done, because even on new builds, because the additional equipment required versus the cost of energy didn't make it practical even at the new build stage. But that dichotomy is changing, and especially when you look at where carbon tax is going and some other things, you know, not only is it something that we're kind of universally starting to do on new buildings, but it's a great retrofit scenario as well. And then, of course, into the conversion, getting into the heat pump design as we move forward. So why, how was NERVA able to put this solution together? Like, what are some of the things that kind of go into this that kind of make it kind of unique? One thing is obviously making sure that between some combination of smart thermostats and temperature sensors, that the whole building we're getting data from the whole building in real time. Because to be perfectly honest, not all areas of the building respond differently. There are, for example, suites on the south sides of buildings that barely need any heating certain days in the winter because the sun is just pouring in the windows, while the north side of the building, you know, probably needs some heating at that moment, right? So under getting all that massive data from inside the building and being able to put it into 3D and 4D models really drives a deeper understanding. And the wireless communication technologies now have gotten so good. And I'm not talking about Wi-Fi. I'm talking about things outside of traditionally what we think is Wi-Fi. But the real-time wireless communication has gotten so good that it is practical to do these type of IoT systems within buildings at a very effective cost, because the sensor costs to come down, the wireless is very reliable, and a lot of times these devices out in the field are battery powered, and the batteries last for, you know, at least a couple years, if not longer, depending on the pull rate. So it really brings together a data package that was not traditionally available at a cost effective, especially if we had to run networking cable or, you know, hardwired communication across the building. But tying that real-time wireless communication into what the mechanical plant is doing and really looking at it from an engineered lens, right? We are engineers here at NERVA. We look at it through an engineered lens, and then translating that into an energy performance dashboard so that not only does the client have real-time and historical insight into their building's operation, but it also allows for when the building falls out of the predicted band of operation, which is typically adjusted based on the, you know, current outdoor air temperature, to understand whether that building has seen a spike in consumption outside the expected band, or even perhaps a drop in consumption outside the expected band. Because as soon as you're outside that band, you'll want to know what's happening here. But beyond just high level keeping energy within a band, all the data is being fed in real times in terms of, you know, this area is not being heated, this fan coil looks like it's failed. So Drulo now with this system is getting additional alarms and notifications, things that previously would have had to have been noticed by somebody and then, you know, called into the property manager who would call their maintenance team. Now, a lot of those issues they're seeing they're seeing and more in real time, and are actually even able to fix them even before the tenant realizes or before there's a complaint lodged. So little bit more detail here, but really getting into this phase one, what are these smart controls doing for this building? Boiler loop temperatures are absolutely critical, right? One of the biggest mistakes we all make in the industry is, we put condensing boilers in and then we don't operate them at low temperatures. Therefore, they never condense. Therefore, their efficiency never approaches the rated. I can tell you this, for all of the buildings in Drulow's portfolio that have condensing boilers, last winter, the maximum loop temperature never exceeded 117 degrees Fahrenheit, which is phenomenal, right? That meant that all the condensing boilers stayed in the condensing range all last winter. Don't get me wrong, I realized that last winter was a very odd winter. It was quite warm, but relatively, but still, we did not exceed 117 degrees Fahrenheit. And that is not just in their newer buildings that have, better envelopes, better windows. That extends all the way back to their buildings from the 70s and the 80s, that obviously are just by in terms of envelope, don't even have as good an envelope or as good as windows. Chillers and cooling towers, maintaining the right flow rate through the chillers and maintaining the right chiller and cooling tower set points so that the delta T's can be maintained. That's one of the biggest problems with chillers and cooling towers. We over pump them through a combination of, not optimizing the VFD speed on the pump and not optimizing the set points. And that causes low delta T's. Low delta T's on chillers and cooling towers are very inefficient. Makeup air operation. This is delivering the right amount of air to ventilate the building at the right time. Delivering more air during heavy cooking hours in the morning around breakfast time and at dinner time, and then turning down the ventilation off hours where it's not as much needed to offset, potential odor flow into the corridors. Certainly fan and pump VFDs support all of those items, and then mechanical submetering as well. So not just measuring, not just relying on the utility bills, or not even just putting in a submeter for all the gas being used by, say, the 3 or 4 boilers in the building, but actually metering each boiler independently in some cases and the chiller independently, so that the real energy data at the equipment level can be cross compared to the operation of the building and to optimize that design, right? And then moving into that phase 2 part where we're trying to optimize the design, some in the existing buildings where possible, and some of these only in the newer buildings if they require more major changes, but right-sizing the new mechanical systems based on the actual operating data we're seeing and not using rules of thumb for design. Getting rid of as much hydronic bypass as we can in the systems, because bypass is a real problem, both from a pumping power perspective. It uses every extra bit of bypass needs more consistent pumping power, but it also, reducing bypass helps control delta T's better, especially in cooling. And really optimizing around part load efficiency and matching the equipment that's running at the plant level to the load of the building. So trying to, if there are boilers in there, trying to, with the boilers, for example, trying to load up a boiler as much as possible before having to turn on the second one, rather than running 2 boilers at kind of half load. That is really an effective strategy. That's all part of this too as well. Doesn't apply as much on the cooling side specific to their buildings, because Drulo, like most multi-res providers, typically only have 1 chiller in the building. So they can't run, there's not 2 chillers running in a pair. But there, the efficiency comes through more just making sure that the flow through the chillers and the set point of the chillers is there to maintain the delta T. So what does this project look like from a roadmap perspective? So our engagement with Drulo goes back to 2019. So this is where we started client engagement. We evaluated their portfolio, really established their motivation and some of their desired outcomes and set goals. And then the first project we ever did for them was 433 King Street in London. So this building actually was a very interesting case. It was a PTAC apartment building that they were actually in the process of converting over to a two-pipe fan coil. So very, very actually invasive retrofit that they were doing over the course of one summer, because obviously with pulling the PTACs out, that took the heating out of the building. So they had to finish the installation of the new two-pipe system and the new fan coils in the suites by the end, by the end of September, and in order to be able to heat the building. But we drove down a 43% reduction in their predicted energy usage, even with the not counting the new system, but on top of the new system that they were already putting in, because obviously a boiler chiller fan coil is much more efficient as a baseline than a PTAC building. So performance validation, that's extending the program with 6 more properties, putting more mechanical submetering in, really validating the forecasted savings versus the return on investment, and then getting deeper into the portfolio, looking at all of those 85 plus buildings, looking at their year-over-year energy data, normalizing that energy data to not only a minor adjustment for where they're actually located, but really normalizing them down to energy usage per square foot type of basis, right? To really understand which buildings in their portfolio were the worst performers and which ones were the best performers. And within that, doing analysis to figure out why are the worst performers and why are the best performers, because within their current operation, it wasn't always obvious. It turned out that, the over the course of those many decades, there just been, a lot of variations in terms of how the buildings had been built, how the buildings had been, controlled with, say, basic outdoor reset controllers, how those curves were set up. And also there was also some major differences within some of the buildings about how the tenants were using the building. And in fact, some of the worst performing Drulo buildings were actually a result of massive tenant abuse. Certainly there was some impact too from, the age of the boilers, the efficiency of the boilers, how the outdoor reset control was set up. That was all a factor too. But the worst buildings we found were actually the ones that had the highest amount of essentially tenants leaving their windows open all year. That gave us the insight to lay out what the turnkey project delivery was going to look like in terms of what we implemented over 10 months, and lay out the continuous commissioning, ongoing optimization, and performance reporting, which continues to this moment of this day and will continue long into the foreseeable future. NERVA actually has a 24/7 monitoring as part of our core services once we implement. So that in, think about it about like, offloading getting a real-time view by somebody outside your organization of making sure that your building is operating efficiently and effectively and not in a failed state, over every hour of the year. Now, in terms of the portfolio rollout, so that built trust, it built results, it built real savings. Then moving to the portfolio rollout, Drulo actually mandated a 12% return on investment and a 15 to 20% GHG reduction. So that was their metric for that's what we need guaranteed. NERVA will deliver at minimum that, and if you don't deliver that, then we as a NERVA will need to reduce our final investment cost and our final billing in order to get to that metric. The reality of it is, as you've, I think, already seen, and I'll reiterate again, we exceeded that. So, which we typically do, and that was the outcome validation. So they asked for 12% and 12% ROI with 15 to 20% reduction. We delivered a 16% ROI with a 36% GHG reduction. So definitely overperformed. Now, as I said, we're in that continuous monitoring, continuous optimization, continuous monitoring phase, and we'll be at that phase forever. Continuous commissioning is really where we need to move most large buildings to. We can't, the idea of commissioning and then walking away and then, not really reviewing the energy data. I mean, maybe not hour to hour, but at least at a, weekly or a monthly level, it's kind of a disservice because we all, I think, know how buildings can fall out of their optimal state, right? Through a combination of poor maintenance, equipment failures, the way the users are trying to drive the building. So only through that continuous optimization and commissioning can we maintain those savings and improve upon them. And then, like I said, now we're into phase 2, using the performance data from their existing buildings to drive and inform their new construction and their capital investments. And then eventually putting together the entire plan for the heat pump, low carbon, zero carbon heating plant conversions that they're going to be forecasting to do probably over the next, at some level over the next 10 to 15 years, with the majority of those probably happening 2030 or later, depending on obviously where the carbon tax goes and how that kind of makes sense, right? We're really at a point today where if you put in a ground source heat pump system, which is obviously the ultimate type of HVAC system, right? Everything else is worse. Your operating costs would be fairly similar to gas, even understanding that gas is, as a market commodity, is fairly cheap right now. But that's today in terms of operating costs. So it's if you're only looking at a year, it's hard to justify retrofitting heat pump systems, even ground source, never mind air source, which are totally cost inefficient to operate right now. But when you look at it over a 20 to 30 year life and you put some assumptions around utility cost escalation and carbon tax, you start to see that the time to invest in your low carbon, zero carbon heating systems is coming, but may not be quite here yet right now. So now is really the time for optimization and conservation before we move to conversion. So quantifiable benefits and impact. Obviously, we've lowered the portfolio's energy costs and GHG emissions. Environmental benefits, reduction of the fossil fuel usage, and the as operating buildings today, less demand on the grid. That's a key one there too. That will come up during the conversion phase when we start to size and install these heat pump systems to get off of the boilers, at least as the primary heating source. Everything we can do to optimize the energy usage in the building, like we've done, drives down the potential need for upgrading the electrical utility feed size to these buildings. Because obviously, as we start to move to heat pumps, we're going to need more electricity. We're going to creating more electricity demand in the building. You want to try to minimize that as much as you can. Obviously, ground source heat pumps are going to use less demand than air source heat pumps, but the optimization that we've done as part of this project is also going to be a significant reduction and will reduce the need for new electrical connections, or at least going to much larger electrical connections. Keeping in mind, we all have to be good consumers of the grid here as we move forward, because the grid is not ready in a large most areas to accept all electrified buildings today. There are grid limitation capacities, so everything we can do to be optimal is a better choice. And obviously giving full visibility into the operational benefits. So here's some of the big numbers again on this project again, but getting more specific. So 1,500 mechanical systems optimized. Across these 85 buildings, we're driving an annual reduction of 3.1 million kilowatt hours and 1.3 million meters cubed of natural gas. And that is, if you put those numbers together, that's what equates to the 36% portfolio-wide GHG reduction. Obviously, most of that coming from the gas. Our electricity in Ontario is fairly clean. It's not perfectly clean like Quebec, but it's fairly clean. But that is still a good number. And if you compare 36% to where most public companies or the public sector wants to be by 2030, which is in the 40 to 45% range, this gets them almost all the way there. So in terms of financial outcomes, this optimization project, we were able to optimize 85 buildings in less than 10 months, which is pretty impressive into itself. And just some high-level things on really the key to practical and financially viable solutions. Because I think everybody gets frustrated, those of us in the engineering and technical space, where we see a solution, maybe we do a detailed energy audit and we follow it up with some more detail and some calculations, and we really see a path forward from the energy and the greenhouse gas perspective. But we've always got to understand that inevitably every decision, whether in the public sector or the private sector, ultimately, in the most part, has to solve financially, unless, of course, there's some kind of outside cash infusion into the project. So energy conservation investments should pay for themselves over time. We're recommending not to jump straight into mechanical replacement. In most buildings, as shown here in Drulo, but also other asset classes, there's a lot of optimization that we can get first before we jump into replacement. And keeping in mind that every piece of mechanical equipment is part of this larger ecosystem, right? And using that data really helps us design better buildings in the future. So with that, I will close out this part of the presentation just with this slide here on the results, and we'll just go from there and open up the floor to questions.
Great, Josh. Thanks for sharing. I have a couple questions, actually. The first one relates to people, right? Like, so you've described that over 10,000 suites were impacted by this project. Lots and lots of buildings, 85 plus buildings. Of course, there are many people that are making use of those spaces. And in some ways, the retrofit that you put out there impacts their lives, right? It impacts their comfort, impacts how they have traditionally used their spaces. What kind of change management activity did you guys have to partake in, or did you do to get them kind of on board?
Yeah, no, that's a very good question, and it's something that definitely comes up, especially in residential buildings. Maybe less so in commercial, institutional buildings, because our home is our castle, right? So it's there's a lot more goes there. So let me describe. So first of all, the installation, what the tenants saw typically in terms of installation to the vast majority of buildings was pretty low impact, right? We were replacing their thermostat with a new thermostat, right? So that, and in most cases, actually wiring in a supply air temperature sensor as well into their fan coil unit, tied into the thermostat, so we get that data too as well, because that supply air temperature sensor in the fan coil unit helps us do a lot of energy and maintenance diagnosis without actually having to be on site. So it's a fairly inexpensive add-on for a lot of benefits. So in terms of the time that we were in the tenant suites to do their conversion was pretty minimal, like usually no more than an hour in their suite, right? And that was obviously all scheduled. But other things we did, for example, was we came up, the thermostats are all the new thermostats are all the same. So we put together instructions or a how to use your new thermostat guide for Drulo to use with their tenants. That, in most cases probably wasn't necessary, but it didn't seem like a hard effort to put it together so that if there was anybody confused. The new thermostats, honestly, very simple to operate, very straightforward, don't really look or operate any specially than the thermostats we were replacing in most cases, and sometimes, in fact, they might even been easier to operate. So not a lot of tenant there. Agreed, though. I would say the biggest tenant impact was around these abusers, right? So after the building got wired up, after all the data was coming in, after 2, 3, 4 months, there's enough data there just to analyze, to really understand who those 5 to 10% of people are who are wasting their HVAC, right? So there was with Drulo implemented an education step there, but ultimately, like the tenants who are abusers do have to accept the fact that if they don't change their behavior, the window and door sensors are going in, right? And that education was more educated from Drulo's side rather than our side, right, as the service provider. But yes, there was some limited impact there. The other impact that was worked around in a few minor cases was part of the savings also comes from too is clamping the temperature range at which the tenants can actually set their heating or cooling, right? One thing you'll notice about off the shelf, $50 Home Depot thermostats is that you can set some really high heating temperatures and some really low cooling temperatures, right? Just that's just how the thermostats come off the shelf. With these new thermostats, that ability is clamped. So there was a few certain instances where the range was maybe opened up a little bit more. One thing I will say that we have found, is that typically the older a person gets, they want more heating and less cooling. It's kind of a very interesting thing that we've found, but we've used that information to kind of target and make sure that if there is an older resident in the suite, that we give them a little bit more flexibility on their heating temperature set point in order to make sure that they are truly comfortable, because that, according to all the data and all the interactions we've had now, is not just something people say. It's actually true. It seems that, like, as we get older, we prefer slightly higher room temperatures.
And those folks, and that's a great observation, and certainly amazing that you guys would work your pro forma to accommodate the age of the occupant specifically. That's really cool. So those people that were the high users, or the use offenders that ended up getting the extra sensors, I'm presuming that you worked that into the pro forma, so like there was no impact on on your project costs, or certainly not a negative one on kind of the performance. Did you find that those folks would attempt to circumvent the controls, or did anybody circumvent the controls, or once they saw and appreciated the benefit, they kind of like bought into the process?
We, to the best of my knowledge, we haven't seen any systematic circumvention, to be honest, at this point in time. We have not seen that. Not obviously, when you're talking about sensors like that, if you know what you're doing, there could be a way to circumvent them, of course, but we've not seen that. At some point, like, the tenants just have to be told the facts, and the fact of the matter is, you're not paying for your heating and cooling directly. The landlord is shouldering those bills. That's typical MERV rentals. And the Landlord Tenant Act in Ontario is very specific to, thou shalt provide a minimum amount of heating in the wintertime. End of story. Right? They're actually, surprisingly enough, there's nothing in our Landlord Tenant Act in Ontario that says you have to provide cooling. And even if the building has a centralized cooling system, if that breaks and you don't fix it, there's no recourse for the tenants, actually, to be perfect, under the law. But heating is regulated, right? So it's not difficult to stay within not just the spirit but the letter of the law, and yet still not allow the tenants to dump heat constantly out their open windows to the environment, right? Like, but part of this too, right? I mean, at least from an engineering perspective, goes to the sense that, like, you do also want to make sure that the building is being ventilated properly. Like, you don't want to put people into a situation where you're forcing them to close their windows to get heating or cooling, but now the indoor air quality of the building is also terrible, right? So that is all part of the discussion on a building by building basis. And in fact, actually, we deployed in certain cases some relatively inexpensive IoT indoor air quality sensors too, just to get some data and to prove a point that the building is being properly ventilated. And the idea that you may want to keep your window open all winter, all summer, or all year round, but that is not tolerable, right? And I mean, sometimes you get through to people and sometimes you don't, but ultimately, like, we all need to take responsibility for our own energy usage. I mean, a simple, in our carbon emissions, a simple example of that could be, it's a 5-minute walk to the corner store, but I get in my car and I drive. No, come on, like we all need to do our part, right? So some people that goes over better than others, but ultimately, let's, we're staying, Drulo and everybody else we're doing this for is staying within the letter of the law, and there's, a logical explanation for why this needs to be done. Maybe not everybody accepts it, but it's something all we can do is just continue to educate.
Sure. For this project, I mean, you described it. There was a lot of work done across many buildings in a whole number of cities. Can you talk a little bit about how long it took to implement the solution, maybe in the context of the whole project, but then also break it down like on a per suite basis? Like what kind of time impact does a project like this have? Implementation.
Yeah, well, like I said, our average installation time in the suite itself, so like in the residence space, was an hour or less, depending on the specific setup of the building. Where was the thermostat in relation to the fan coil? Was there enough wires between the existing thermostat and the fan coil, or did we have to pull a new cable, right, in order to increase the wire count, right? So it certainly varied, here nor there, but on average, our one of our technicians was typically doing 8 to 10 suites a day. So that was the suite effort, and that actually was separated in terms of execution from the plant effort, right? So we had certain crews who were specialized in getting into the suites, being, with all the things that go around that, right? Like pre-notifying the tenants that you're going to be in there, which is a requirement of the law and all that type of stuff. And really, really just focusing on that rollout, while we had other crews focusing on the plant controls, which they don't, because both of those don't have to come online at the same time. You can get one done before the other and then just meld them together at the end. So the order of execution between the suites and the plant wasn't necessarily that tied together. The plants, they take days, right? Because you're running conduit, you're installing new sensors, you're pulling new cables, you got a new controller going into the plant. And again, like not every building is the same, so that varied on time, but there was definitely, at least a few to several days of a crew of probably 2 invested into the plant, while each of our techs were doing 8 to 10 suites a day. And that kind of pace is what allowed us to do all 10,000 plus suites, the core of the work, at least within a 10-month period, and get that rolled in, right? So I mean, if we extend that to what's possible across all MURBs in Canada, I mean, there's a significant fraction of the GHG reduction we can deliver for the entire country, that can be delivered for the entire country, really probably driving down two paths. This path here through the MURB sector, the other big path that I'm not going to get into obviously today, but the other big path that really hits the vast majority of buildings is optimized controls on rooftop units, your standard rooftop unit. Like, we all love big buildings, right? We all love Class A office buildings. We all love big institutional buildings and all that kind of stuff. But the path to decarbonization is through mass retrofits, not one-off retrofits, right? So that's the other place that actually NERVA is working in the rooftop space as well, to try to drive mass optimization through standard gas DX rooftop units, which eventually will not be gas DX rooftop units. We're going to have to turn those over to, in most cases, probably air source heat pump rooftop units with gas back.
Yeah, well, we'll look forward to what you come up with in that regard in a future conversation. For this project, did you have a standardized, or what was the standardized digital platform for integrating all of your controls? Like, is it something that you guys have written on your own, or did you use something from the market?
No. So the hardware is actually off the shelf from multiple vendors. So I'm not going to pigeonhole it to specific OEMs, but it's a mix of off the shelf, open API type of hardware that we internally engineered to work well together, and then put our programming and our thoughts in terms of algorithms into the hardware to make the whole buildings work, right? So, you know, we're honestly, the hardware is kind of the second thought, to be perfectly honest,
Okay.
right? When we think about optimizing buildings, we start here at NERVA from a theoretical perspective or a best in class perspective. Best, if I just forget about what I can do, or forget about just the specifics around the programming, but it's like if I take all of the practical solutions that exist to optimize HVAC energy usage within, specific to the building class. For example, in a multi-residential building, there's no play for CO2 on demand control ventilation, right? That doesn't exist in this type of building. There's no way to integrate that in because of the way the building's done. Corollary, on the rooftop play, a lot of the savings you can drive off a standard gas DX rooftop are driven just by implementing CO2 DCV along with some other things. But it's really taking that theoretical point of view, mapping out the best in class, and then translating that into algorithms and putting those algorithms onto open hardware that is readily available in the marketplace to make the system work. So not while we have our favorite hardware, we're not tied to hardware. We're tied to algorithms, and we're tied to, even before algorithms, best in class solutions, real best in class solutions for how buildings should actually operate.
Okay. Interesting. Switching a little bit of gears, but staying within multi-unit res, have you guys come up with or determined what the best practice for decarbonizing domestic hot water is?
Very good question, and one I'm glad to answer, actually. So domestic hot water is a tricky one, right? Because we're typically trying to generate and hold that water at 145 degrees Fahrenheit or somewhere around there to avoid Legionella risk, right? And the problem is that most commercially available heat pumps don't operate that well. Air or ground source don't really operate that well above 120 degrees Fahrenheit hot water, if at all, right? So it's not that there isn't high temperature heat pumps out there. Of course there is, but the performance of them is not terribly great. So there's a couple things, actually. I mean, obviously the easiest solution to decarbonizing hot water is electric hot water tanks. Just pure electric resistance hot water tanks. And if you look at what a lot of people are doing in the single family home market, that's the direction they're going, right? It's kind of the first choice for there. But that solution doesn't necessarily scale very well for larger buildings when you start to have to think about, the feeder size into the building. Yeah, and it also doesn't typically scale that well from an operating cost perspective these days, because because again, like the domestic hot water heating is paid for by the owner, not by the tenants in most cases. So it really would increase our operating costs pretty heavily. The in-between solution that doesn't necessarily rely on outdoor heat pumps. I mean, you can certainly do heat pumps, air source, ground source heat pumps, and even if the heat pump doesn't get you all the way to 145F, maybe get the heat pump to get you to 120 and then use electric boost just to get you the last few degrees, right, as you're coming in. That's one possible way to go. The other interesting way that we're seeing a lot in the single family home market, and I expect to see more of it in larger buildings, is indoor air source heat pump hot water tanks. I don't know if you're familiar with those, but they are an off-the-shelf item now, where essentially it's an electric hot water tank with a small heat pump on top of it. Mm-hmm. It's really a direct swap out for most conventional hot water tanks. Um, and you know, the indoor air source heat pump is essentially stealing a little bit of heat from the indoor air. But in the case of multi-residential buildings, you know, that often is in the mechanical rooms, which are hot anyways. So you're actually kind of doing heat recovery in the mechanical room. Or in the case of a single family home, it's usually in your basement. It may be an unconditioned basement. So you're not really losing much down there. So that's kind of a very interesting solution. And if the heat pump on those integrated tanks, electric tanks, can't keep up to the instantaneous demand, then it does switch back to pure electric resistance mode. So if you've got, like, you know, everybody wakes up in the morning, you got 3 or 4 showers in a row, you know, and the heat pump can't keep up, it'll do electric resistance. But then over the rest of the day, the heat pump will operate to for the, you know, varying loads or the recharge. So that's a really good one. I mean, the other one that you can see more specific to multi-res is a lot of newer multi-res buildings, not Drulos, they're still using fan coils, but a lot of newer multi-res buildings are using in-suite heat pumps, water to air heat pumps, supported by a boiler, a cooling tower. So one not full decarb path there, but a partial decarb path is instead of firing gas to directly heat the hot water, putting a water to water heat pump off of the loop that's already being supported by the boiler cooling tower, that can offer some, not just efficiency, but actually in the summertime, when the when the heat pumps in the suites are in cooling mode, then the water to water heat pumps can take that heat from the loop to create domestic hot water before it needs to get rejected to the cooling tower. So you can almost kind of get, like, not, it's not free because you still have to invest some electricity, but you're getting nearly free hot water in the summertime when you've got that cooling load in the building that you can recover before rejecting it to the environment. I mean, just to close up this section here, right? One thing that we always got to keep in mind as energy people, every time we see a cooling tower, it's a waste, right? I'm not saying it's always avoidable, but the fact is a cooling tower is designed to reject heat to the atmosphere. We should be doing everything we can to try to recoup that heat back into the building. I know it's often low grade, low temperature heat, but we should be trying to do whatever we can to recoup that, because every time we're rejecting the environment, that heat is gone.
Yeah, you bet. I mean that's the role of the heat pump, right? So you can play with low grade energy sources, you know, with a heat pump. That's fantastic. Great. Listen, I want to kind of be a little bit more philosophical with my next question. It may be the last one. We'll see what comes up. But you spoke a little bit about optimization first and being, you know, the strategic, you know, best first step that we can take, you know, along this broader decarbonization journey. And I don't disagree. You know, I think, you know, there's been many studies done, and of course there is lots of opportunity to invest capital and make substantial reductions in carbon. But you know, the reality is, the sobering reality is that takes money, and not all organizations or people have the money to do it. So optimization is a great first step. But if you flip the coin over and you take the devil's advocate position, if we focus on the optimization path, are we making the next step in that journey that much harder to justify? If, you know, if we're more efficient, are we going to make the ROI on the capital project later on harder and less palatable? What do you think about that?
Well, I would argue the opposite of that. And the reason is because, you know, just using some round numbers here, if you drive out 30% of your heating load out of the building through optimization, and then use that real data to inform the size of your low or zero carbon heating plant that you're going to build eventually, you've just reduced the size of that investment on the far side. That's fundamentally, in my opinion and Nerva's opinion, why optimization has to be first. We can't, if we just go out and just install heat pumps everywhere, they're going to be too large in most cases. And so we do have to look at you do have to think a little bit longer term here. I mean, certainly there's the simple payback on just the optimization step, but essentially what you're doing is through optimization of any type of building, you're setting yourself a new baseline with real data that allows you now to really inform the sizing of your future heating cooling system conversion to different sources. That is the optimal way to go, because the idea that we can do the old rule of thumb, for example, and here I'll put some real numbers to this one. So it is not that uncommon in the past for engineers to size the boiler systems for these multi-res buildings to somewhere between 25 to 30 BTUs per square foot installed capacity, right? Now, that is a general rule of thumb I've seen in so many buildings. And I'm not saying they were wrong for doing that. Realistically, the buildings never operated at that high level. That number does include obviously some redundancy. Nobody has a building where that doesn't have at least like one extra spare boiler, just to compensate for downtime. But it's still too high. But we accepted that over the years because really the cost of adding additional boilers wasn't that big a cost, right? Boilers have never been terribly expensive. So we just kind of accepted that, and it produced buildings that would operate, pretty reliably and ultimately would not incur much, if any, liability back to the engineers for non-performance of that building, whether that's the first year, 5 years, 10 years down the road. But the reality we've seen from Drulo, to get into some specific numbers. So I said that, the traditional rule of thumb on boiler sizing in these types of MERV buildings was 25 to 30 BTUs a square foot, peak, ultimate installed capacity. We're not really seeing operating values in these Drulo buildings, all ages of these Drulo buildings now, higher than 10 BTUs a square foot. So even when you build 50% redundancy on top of 10 BTUs a square foot, now you're only 15 BTUs a square foot, not 25 to 30, right? But the 25 to 30 was acceptable when we were just putting in simple, cheap boilers. But the delta in cost between a 15 BTU per square foot heat pump system versus a 25 to 30 is massive, right?
Sure.
So,
but are you not in that argument though? Are you not making the broad assumption that if somebody was to do a capital project first, that they would size their capital project based on the existing installed capacity rather than doing, as you're describing, the engineering work to right size the solution? And don't take me the wrong way, Josh. I'm not disagreeing with your position. I'm just trying to look at it from multiple perspectives.
yeah, well, no, I agree. Let's look at it from that other perspective. So I'm an engineer. I've been asked to either to do the project, either to replace the boilers or replace the boilers like for like, or replace the boilers with a new heat pump system for this building, right? One of the first tenets about in professional engineering is liability. It's kind of always been at the top. So I never want to put myself in a position where the system that I'm designing and that will be installed will underperform, will underperform for the building, because that's risk, and it's real risk, right? It's real risk.
Mhm.
So we've tended as an industry to kind of trend towards the liability side of things, and when it didn't have that big a cost impact, like on like for like boiler replacements, it wasn't really something that had much benefit to talk about or be analyzed. But now let's say that we've recognized as engineers that we do need to tread the line between efficiency in terms of energy, efficiency in terms of capital, and liability, because there is a line in between there. Not all that different of the line that we hopefully all realize now between energy efficiency in buildings and indoor air quality. I tend to think that before COVID, we maybe didn't put as much. We were doing things in efficiency that were maybe negative, a little bit negative to indoor air quality. But obviously, the pandemic opened up our minds to we have to tread the line in between. It's no different with this in terms of ultimately, heating, cooling plant sizes. But the thing is, and I appreciate this about engineers, is that to make that jump theoretically is maybe not difficult in your mind, but ultimately, in order to satisfy the liability concerns, the real data is what comes into play, right? Where has this building actually performed since, before optimization, after optimization, and is the engineer willing to hang their hat on the real data? That's the best proof that you can provide to anybody that will help them inform their designs.
Yeah, you bet. So essentially what you're saying is you're turning this project, well, you're using the living lab philosophy. So you've taken the building, you through optimization, you've made it a whole bunch better. You've gathered some data. Now you know what your true loads are. In the future, when Drulo decides that or when the boilers or whatever other pieces of equipment are there, they reach the end of life, they require replacement. Now you've got X number of years of real operating data. You can run all sorts of regression on it, and you can right size their replacement. And hopefully the ROI for that project is also in a palatable range. Am I reading you right?
Exactly. I would
Okay,
like
right
to
on.
think at that point we've done everything we possibly can to put the ROI into a palatable range. Understanding that the ROI on decarbonization is also dependent on factors that nobody has a crystal ball on, right?
Yeah, you
Carbon
bet.
tax, utility cost escalation, right?
Yeah, for
Those are
sure.
things that you have to have frank discussions about because you have to agree on those numbers. Is it 2%, 3%, 4% on the commodities, electricity, gas? Is the carbon tax going to tap out at $170 a ton in 2030 and stay flat? You obviously those assumptions are also key to that that path forward. But definitely, like, you need to, when you go down that route, you can't look at it as a 5-year, 10-year. You need to look at it as at least a 20, if not 25 to 30 years, really trying to capture the full life cycle of the investment that you're making over time, because there is the capital cost, but you have to look at that delta in operating cost over the expected life of the equipment.
Yeah, for sure. Wonderful. Well, listen, Josh, I really appreciate that you took the time today to give us kind of the details and in the summary of this project. It's an exceptionally large living lab example of the potential that efficiency plays. Efficiency being the untapped utility, I guess some people have said. And I really appreciate that you've given it and kind of given us a little bit of a peek onto the inside. Hopefully those who have watched or will watch in the future the recording will gain a little bit of inspiration out of the work that you've done. Perhaps ask themselves some tough questions, or maybe see applications for this strategy, in their own portfolios or with their clients' portfolios. So thanks for exposing us to the work that you've done, and hopefully it, like I said, inspires additional projects just like it.
Yeah, thanks for the opportunity, Andrew. I greatly appreciate it.
Wonderful. Anyway, thank you. Thanks everybody for tuning in. I hope you found some value in it. And again, thanks to Josh for taking his time. On to the next one. Have a great day.